Another key recommendation from the original Welfare and Safety of the Racehorse Summit was the establishment of a dedicated lab to evaluate track surfaces. As a result, the Racing Surfaces Testing Laboratory has now been operational for over a decade. The lab has improved surface standards by offering testing services, collecting and storing maintenance records, and assessing weather and wind data. Dr. Mick Peterson, Executive Director of the Racing Surfaces Testing Laboratory and Professor of Biosystems and Agricultural Engineering at the University of Kentucky, will share an approach to expand and accelerate surface safety programs for improved racing surface consistency.
All right, let's see if I can be the one person who doesn't have a problem with the mic. That'll be my job. What I'm going to start out with is I'm going to, actually Dr. Johnson queued this up pretty well for me by going off script. So you got kind of an introduction from the McKinsey and Company, Dan Singer, about sort of this consistency issue, the importance of consistency on racetracks. And I want to step back because I originally got involved in racetrack surfaces because I was working with Wayne McElraith at Colorado State on exercise-induced arthrosis, and he talked about that on the last Welfare and Safety Summit. I want to revisit some of those things because I've learned a few things in the last couple weeks that have updated some of the things that I understood previously. So the first thing I'm going to talk about is fatigue, failure, and bone, and then we're going to talk about the results from the pre-meet inspections under HISA. Then where we go from here, and this is the real-time moisture measurement, advanced water truck, and then really the holy grail is next-generation surfaces for racing. Finally, I'm going to go back and say what I say at the end of every talk I give. Risk is multifactorial, and we need to pay attention to all the risk factors, and surfaces are just one of them. So speaking of going off script, here's where I'm going to start out with. I'm going to start out with coiling suspension springs for automobiles, where I started my career in that little dot in the middle of the factory that employed 30,000 people. There were 400 people in the plant. We did high cycle fatigue, and at that point, in the early 1980s, we had the Chevy Chevette, which had tapered wire, and they used to joke that the springs were broken by the time they got off the assembly line because they were so poorly designed. My first job was working on the 86 Buick H car, which was a progressive rate spring, and we went from 100,000 cycles, where they would compress it as far as they would compress the suspension in the car, 100,000 cycles. The specification went up to 1 million cycles. We were looking for a really rare event. We were looking for a very durable spring. This kind of sounds familiar? Now you can make a spring last forever, but it's going to be very heavy and very expensive. What happens when you have metal is if you use low enough stress, here's the number of cycles, it's logarithmic. If you look at the stress, if you lower the stress enough, it lasts forever. All right, why don't we do that? Because it'd be heavy and expensive. Okay, so metal and ceramic fatigue occur when there's a repeated elastic loading. It doesn't have to permanently deform. It's not like you're bending a paper clip. You can just use the paper clip over and over. These are, what happens is defects in the crystalline structure that are called dislocations or microcracks coalesce to initiate a crack of critical size. It's all in the elastic region here, and interestingly enough, this is a stress-strain curve from bone. And to remind you, if we don't use it very much, it won't break. So, will only slow or lightly raced horses not have a catastrophic injury? So this is the model, and I have to give credit to Dr. Chris Whitten from Melbourne. He got me started thinking about how we could look at this. Okay, if we look at the damage on the vertical axis, every time you do a fast work, you create damage, and the damage will accumulate. This makes it look like it's a one-dimensional process. We know a number of timed works, we hit the injury line, and if we're lucky, well, if we're unlucky, we have a catastrophic injury. If we're lucky, there's veterinary intervention in that moment between the injury and the catastrophic injury. Well, what does that do for the welfare of the horse? The most you could hope for on this is to change the slope of that, to make it a little shallower so they could last a few more cycles. And remember, the veterinary intervention is absolutely critical under these circumstances. You've got that moment in time between injury and catastrophic injury, and it may not be very much. But bone isn't exactly like steel. Now, veterinarians have used this analogy, and the worst thing that happened to me was when Dr. Edwards, a couple weeks ago, a mechanical engineer, used the same analogy and said, bone's just like steel. It's just going to fatigue it, and it's going to fall apart. And I thought, okay, this is more bad news. And now I've got the mechanical engineer, like me, who's agreeing with all the veterinarians who said this. But preventing bone stress injuries in runners with optimal workload, it's more complicated because we're talking about tissue. So bone is not steel, it's living tissue. So is fracture inevitable? This is a graph that Chris Whitten put from University of Melbourne. And we got some ups and downs there. That's the key. Because we've got damage, but we have remodeling. So, how can we control the amount of damage and provide what's needed for the horse to recover? And we're going to ask a lot of the trainers and the veterinarians to understand this process, so that's where surfaces come in. The surfaces can't be this random thing that changes every day. But the goal then will be to avoid the injury and certainly avoid catastrophic injury. So our model of lifetime health goes from this to this. If we think about the early months, we're building a healthy horse. We look at the racing career, we're avoiding severe injuries, and then keeping that horse sound for a second career. Training, recovery, and we keep damage below the level of injury, and we keep damage well below the catastrophic injury line. But we need to be able to provide the trainer and veterinarian with a consistent surface to work with, because they're having to make the decisions on the behavior and the health of the horse. The other thing that's important here is it's not just the racing surfaces, it's the racing and training surfaces that are going to affect that training and recovery. So we can't have new uncertainty that's introduced by the track. So people say, why is a consistent track important? A consistent track is important for the trainer to be able to make decisions, as well as to control the amount of damage so that recovery can be managed. So the primary load, the other complicating factor on this, the primary load and the damage is from muscle-generated force. It's not the surface. Muscle-generated force is much larger. And so what's happening is you've got this muscle-generated force, but it's different. The horse is adapted to the muscle-generated force, because as the horse is building the musculoskeletal system, they're building it together. And the uncertain part of it is the ground reaction force, or the surface. So, to quote a famous movie, we're turning it up to 11 with the surface. When the surface is uncertain, we are going to create the uncertainty in the overall loading. It's that last little bit, turning it up to 11. So consistent and training surfaces allow adaptation to the surface. Okay, so then we go back. What are the sources of variation in the surface? So there's the long-term changes and the short-term changes. Long-term changes are, for all surfaces, our base profile, consistency, the grades on the tracks. For synthetic and dirt, there's a hard pan and there's the composition. And for turf, you still got to grow grass and you have thatch and compaction. This is what we've done, and we've got infrastructure in place. Much more difficult is what Dan Singer from McKinsey & Company was talking about, are these daily variations. Dirt, moisture content, cushion depth, turf, moisture content, and penetration resistance, and synthetic, subsurface compaction, creep, and the temperature of surface. This is a lot bigger challenge for us. The maintenance quality system was developed as a part of the Racing Surfaces Testing Laboratory and the other entities that were put together. And there's 3 stages of this. This is the process for maintaining the surface. First one is documenting what you've got, figuring out what surface you've got and what you're going to use it for. Second one is a pre-meet inspection, phase 2. Daily monitoring is the third one. This data goes into a database. What happened was the MQS and the related research contributed to the 2020 rewrite of the surfaces code for the NTRA Safety and Integrity Alliance. Then in 2022, these same ideas were integrated into HICE's framework. Sometimes we're hypercritical of the industry because it seems like things don't necessarily work smoothly, and this probably really stands out as something that worked very smoothly. In 2019, NTRA gave a gift to the University of Kentucky for research space and equipment, and a space to calibrate equipment. 2020, the Jockey Club gave a gift to Racing Surfaces Testing Laboratory to consolidate the organizations and update equipment. So what happened was there was infrastructure research and equipment for standard track testing that was just waiting for the HICE regulations. This was focused very much on the seasonal, that phase 2 of the MQS, or pre-meet inspection. There was equipment based on the West Coast, which is located out there that can be used for testing West Coast tracks. There's a single nonprofit laboratory. And in 2023, the phase 1 and phase 2 of the maintenance quality system not only included the HICE tracks, we saw many of the non-HICE covered tracks participating as well. There's a really limited constituency for bad or inconsistent race tracks. So far, I haven't found anybody who will advocate for it, but that's a very limited constituency. But the timing on this couldn't have been any better because you notice the infrastructure was in place before the regulations. So if we look at the longer term resources, longer term changes of the track, these resources are in place. So let's look at what the pre-meet inspection is. We have a biomechanical surface testing that replicates the speed and force of the leading four-limb at gallop, 2.5 times the body weight. We make measurements like it was off of a hoof. But here's where it gets exciting. If we look at 2023, we now are looking at 47 racing surfaces. Remember what the McKinsey and Company discussion was. We don't want variation between tracks. If you look at this bar whisker chart, you can see the average, you can see the variation, and you can see the range. So what's our goal on this? Our goal on this is when you ship from one track to another, and you start out the race meet, it's going to look like wherever you came from. And it's going to have the smallest variation possible. So once we've got this, and we've got averages, typical variation, if you're beyond that typical variation, we start diagnosing problems. We use ground penetrating radar. This uses radar pulses to image the subsurface layers and find approximate layers. So there's the cushion, where the hoof goes down to, the pad that supports it, and then the base, where we can all see. And this actually has a drainage pipe in it, below it. We've got the same thing there. We can see how consistent the cushion is on the track. Think about this. When you start talking to a construction company, typical racetracks, the cushion depth is held to within 1/4 of an inch. Mile long, the racing lanes, let's say 50 feet wide, and the depth of that cushion around there is within 1/4 inch. That's what we're seeing. The ones that are 1/2 inch, we're saying, look, we need to diagnose the problems. This is the level of consistency that we're already achieving, and we need to get better. The other thing is grades. Again, the McKinsey this morning was talking a little bit about this. You can see the grades on the straights, and in particular, the variation of the grading on that. This is important because it affects the drainage of the track as well as the biomechanics of the horse traveling. So if we look at the sources of surface variation, these longer term changes, we're beginning to get a handle on it. And here's the thing that's really exciting about this. The information goes back to the superintendents to fix it. Our goal is to be there 3 to 5 weeks before the start of a race meet. The goal is to get things fixed before horses are on the surface, before they're training or racing. And we make use of the expertise of track superintendents so they can compare notes. So we can refer to other superintendents who are in the same region or have similar tracks so that they can compare notes. The harder part is this daily tracking. If we look at this, we've got the moisture and cushion depth. This is pretty low tech, but labor intensive. You're measuring the cushion depth, you've got a moisture meter. Turf tracks, once again, moisture shows up, and we've got the penetration or going stick. This is the Longchamp penetrometer on the right. And then synthetic, it's temperature and penetration resistance. Again, all these ideas are embedded in the HISA regulations. So as we move forward, the participation, the engagement, it's there. What's missing at this point is the high quality data. So tracks are reducing the day-to-day variation. They do turf track drainage and irrigation. They can maintain a wet or drying dirt track. And they improve the grading so that when the water runs off, it runs off consistently and reduces variation on the track. We also repeatedly find that what we have to do is we have to adapt the track to whatever moisture. So some tracks have engaged intensively in this process. Churchill, for example, every day between training and racing takes 96 points for moisture on the main track and 84 points for moisture and going stick on the turf track. That's walking around, taking all those measurements, uploading it to the database, getting back your plot, looking at it. It's labor intensive. They also enter, like the best tracks do, every time a piece of equipment goes out on the track. These are the veterinary records. And again, it's labor intensive. It's every time a tractor goes out, it's the settings, it's the speed, it's whether they use the float or whether they use the harrow. If it's the harrow, if it's the float, whether it has a back brake. But here's the tough days. The tough days aren't necessarily the days that you look at it and you say it's wet out there. On Oaks and Morning of Derby, it was floated for the Oaks in training, and then they used chain harrows behind the floats, and in New York it'd be a back rake. New York and Keeneland it would be a back rake for the first races. But on Kentucky Derby this year, they had to switch to the harrows mid-card because the track was drying out, and by the time they got to the end of the race card, if the sun hadn't been going down, they'd have been out there with the water trucks. Think about those decisions that you're having to make in real time. It's a Kentucky Derby. You're obviously dependent on the expertise. There's no substitute for expertise. It's no different than advanced diagnostics for a veterinarian. You want to supplement the ability to use those things on the end of your hands. But this is where there's more information that's needed for the decision making. So what does moisture do to a racetrack? What does moisture do to dirt? This is the range of moisture that would not be unusual. This is probably about the range of moisture that you saw over Derby and Oaks. It probably went from 14% to about 8% is probably a reasonable number. The shear strength, or the ability to support the hoof as it goes into that surface, was reduced by 35% in that range of moisture. You know that from knowing what a wet surface looks like. You know it changes dramatically. And what's particularly challenging is it drops back off when it gets dry. You just can't get it wetter and wetter, or you can't just get it drier and drier. It's got to be just right. So, a strategy for improved racing surface consistency. Better daily track measurements. You saw what Churchill's doing. You saw how labor intensive that is. But this is only daily measurements. We need to improve that first. That's the first thing that needs to happen. The water trucks are incredibly expensive, incredibly complicated, and used inconsistently and modified inconsistently in the industry. And then real-time moisture sensors. Okay, what about daily measurements? Great series of paper. You know, and my attitude on this is you don't do anything unusual. You look at what the literature says, you copy whatever's there, and you try to improve on it. In New Zealand in 1996, they decided that the penetrometer worked for handicapping. The punters could sit there and look at the penetrometer, and it's just the raw data. It's not modified, it's not turned into a number. The numbers are just used. But in 2022, because they'd been taking this data every day, they showed that the penetrometer could be used to predict surface risk. No other device on turf has been shown to correlate to speed or either speed or risk. The other thing we know that we have to measure on dirt and turf is the cushion depth, which we can also do with the penetrometer, temperature on synthetics. So this is the integrated track tester, the Longchamp penetrometer for turf and cushion depth. It's got a moisture sensor with salinity correction and a temperature sensor. This is data that comes off the penetrometer and moisture sensor. It replaces all the manual measurements with one device. It automatically uploads, and it's consistent between users, so it not user dependent. The other thing is, it's now in the public domain. Everything we've done at Racing Surfaces Testing Laboratory, there's never been any patents or anything, it's all in the public domain. So the objective of this is to push this out into the industry to be produced by multiple vendors that can supply the industry. Not to control it, not to sell it, there's no product here. There is a concept and a design that then can be modified. The next item on the list was next generation water trucks. Not surprisingly, if all the nozzles spray the same amount, it's wet on the inside of the turns and drier as you go out because it doesn't go as far. We can't, with most water trucks, there are exceptions, apply a partial load evenly. Shaded areas are wetter, and we depend on the talent of the driver, there are some good ones out there. And the other problem is water trucks are outrageous. It's a $250,000 piece of equipment that rusts quickly. So, a standard water truck design in the public domain has the potential to reduce the cost to the racetrack to replace their water truck, and by standardizing the design, as we begin to implement instrumentation, it does not need to be custom designed for every racetrack. As there are improvements that are made, a standard design. Again, leaving it in the public domain. Here's one of my favorite ideas. I know it's used outside of the US quite a bit, is putting the whole thing on a hook loader chassis so you can lease the chassis. This is not for this audience or necessarily. This is the sort of thing that's very engaging for a racetrack manager, the idea of being able to lease the chassis and not have to own something that's going to rust quickly. So a hook loader water truck has the opportunity for the arm design would be specific to the application. Sensors could be added to a standard design as needed. Lease chassis, or purchase a replaceable chassis to keep the water truck. And construction could be done locally or bid out and shipped. And again, the design in the public domain. Keeping in mind where we're going, the industry needs to support the idea of there's a standard of care that the tools are in place and the tools are available. All right. This is probably the most important one, though. This is where we started. This is the Kentucky Derby, the judgment. It's the advanced diagnostic imaging for the racetrack. Track moisture, we need every race, not once a day. We've done it. We've done the real-time moisture from a harrow. We harrow between every race. So you've got a piece of equipment out there that can carry the moisture sensor. You also get, for free, harrow speed, harrow settings, and GPS coordinates. Every time the moisture is on the track, you get the data. You see images done there on some tests that were done at Laurel. The sensor, however, anything that contacts, keep in mind, the most interesting times are when the track is getting sticky and drying out or too dry, and those are the times where the sensor itself loads up and has problems. So there's a challenge here. We got the data, but it needs to be non-contact. Whatever we're doing has to be non-contact. Real-time data, then, we've already built some of the infrastructure. Using the integrated track tester, we already have data going up to Amazon Web Services that automatically generates a report in real time back. And if we have the right sensor, we can use that infrastructure in place. So the existing contact sensor loads up. There's an additional challenge in that we need to see underneath the surface. The hoof prints, we need to see the moisture content to the depth of the hoof that's penetrating into the surface. We've got several design options. There's P and L band radio. DoD and some satellite applications use that. Ultrasound or sensors on a harrow tooth. So research plan on this is, going back to this infrastructure we have in place, is controlled moisture and variable profile in the NTRA lab, making use of existing ultrasonic infrastructure, and then focus additional on P and L band radio using a partner spinoff from University of Colorado. And then, as I mentioned before, integrated into the infrastructure that's used on the integrated track tester and the water truck. So we've already gotten Plasma as the standard IoT platform for racing. This data automatically synchronizes up with HISA. The data goes in real time. That includes the data coming from the manual data entry or anything that we've got coming in, including the weather stations. If we have the penetrometer, we have cushion index, trap temperature, surface temperature, and GPS. With the water truck, we'll have tank level, pressure, application rate, speed, and GPS. And then the harrow or the non-contact sensor would be the real-time track moisture between races, speed, and GPS. This then can be integrated into that database that goes back, synchronized with HISA, and then can be used as a part of the epidemiological models. So, kind of repeats, sorry. Non-contact, can't load up when you need it most. More than surface moisture, cannot use visible or infrared, and needs to work on the big days when there's a lot of noise. So LP or S band is a microwave frequencies, and these are what we're looking at right now. The L band is 1 to 2 gigahertz, 8-inch depth of penetration, 8-inch wavelength. That's in this kind of the sweet spot. That's probably a little deeper than we need. S band, 2.4 gigahertz in wavelength of about 4 inches. The other option is a near infrared or optical sensor on a harrow tooth. The other option is acoustic, because acoustic waves, like microwaves, are a function of wavelength and frequency. At 40 kilohertz, we go in about 1.5 inches. At 15 kilohertz, we're at about 4-inch depth. We've already shown that we can separate out the layering here as well, and so the opportunity presents itself to be able to measure the depth through the hard pan. Design issue work plan, depth control accuracy. We need to understand whether we can get the sufficient accuracy and whether we've got the wide range of moisture content saturated to drying. Surface roughness is a challenge because it's smooth when the track's floated, gives you very different readings once you've got a harrowed surface. And then the electromagnetic radio interference. The only way to test this, and we've proven this over and over, is to do it on big days when things don't work because of NBC or Fox Sports. So what's status of the racetrack maintenance? HISA and the superintendents are making dramatic progress on things like grade measurement and maintenance. Dennis Moore at Santa Anita has been talking about this for a decade. And now we finally got an appreciation on a bigger scale. You saw that in the McKinsey and Company report. This really matters. Racetrack design, consistency between racetracks. Southern California demonstrated the effectiveness of consistent design and consistent maintenance between racetracks, and that's been one of the factors, as well as the veterinary protocols. And also some things like standardizing harrow designs regionally. This is the data for decision making. New efforts, however, are needed for continuous improvement. Better tools for daily measurements, more advanced water truck design, and real-time measurement of moisture. This is better data and better decision making. And then the final thing I want to mention is next generation surfaces. As we get this data, we're going to begin to understand what the horse is looking for. Right now, we're just looking for consistency. I think there's a really strong argument for consistency. But at some point, we need to step back and say, what is the horse looking for? What is the optimal surface for the horse? The optimal surface for the horse goes back to this picture. We want to understand what's happening during the damage and recovery, the training and recovery process to extend that career so that there's a second career. These next generation surfaces need to be able to deal with water, hydrophobic like synthetic surfaces, or control the moisture. Biomechanically, they will probably mimic turf more than anything else, because I've rarely heard anybody say, my horse doesn't like the turf. Sometimes the turf isn't good, but you don't get a blanket, my horse doesn't like turf. Start with improved maintenance, but the data, the big data question on this is learn about the optimal biomechanics. As I mentioned, going to finish up pointing out, catastrophic injury is multifactorial. Racetrack surfaces affects every horse in the field, but these other factors contribute to it. Our goal on consistent surfaces for racing and training has to be provide a surface that the trainer and the veterinarian can make the appropriate decisions, because Wednesday's surface looked like Tuesday's surface and looked like the previous racetrack surface. I want to thank the people who provided ongoing support for this, and thank you.